So welcome back to our latest lecture session. I guess we have been discussing aqueous complexes in the last couple of sessions. So we'll continue that discussion for 2 more sessions and then move on to precipitation and dissolution based reactions. Yes. So let's just recap what it is that we have been discussing about the aqueous complexes. So in general, let's say as an environmental engineer, let's say in which scenarios would you be concerned with aqueous complexes now, right? In general, when you have metals, right, we saw that in the presence of an electron rich compound, which we are saying is a ligand, right? We are going to have a formation of aqueous complexes. So the metal is the electron poor, right, compound, and the ligand is the electron rich compound, and it has a binding site. And depending on the number of binding site, I guess we had different terminologies, right? I think multidentate or monodentate and so on. Yes. So anyway, so what are the applications, I guess, right? So let's just quickly recap that. So one is that, let's say if it's a toxic metal, as in if the free metal is toxic, right? So by addition of, let's say, an appropriate ligand, you can form complexes. Again, here the assumption or the scenario is that the free metal is toxic, right? So if you add a ligand, your concentration of the free metal is going to decrease based on obviously the appropriate choice of the ligand, right? And why is that again? So let's say initially when there is no ligand, let's say, and let's say X is my metal, and X total is only in the form of the free metal, let's say, X plus Z, let's say, there's a random example here. But let's say if I'm adding a ligand here, let's say, X total is still going to be the same, right? But here I'm going to have lesser concentration of my particular free metal, and then I'm going to have the relevant complexes here, right? So thus, as you see, the X1 concentration is going to be less than X, right, without the complexes, right, or the scenario when we have no complexes, and thus you see that, or you can observe that the toxicity of the particular system can be decreased. Let's see, again keep in mind that as you remove the metal, again it's an equilibrium, so the equilibrium is going to shift towards the left and so on, but those examples we are going to come back to later on. And obviously another aspect I believe we discussed was it can also affect the solubility of the metal, and in general, as we discussed earlier, aqueous complexes are relatively more soluble, right? And let's say if you have a metal whose concentration is or which would precipitate out at low concentrations, let's say, but you want to have a higher total metal concentration in your particular solution. So what's one solution? Adding a ligand, right? So that even though the free metal concentration might be less, the total metal concentration in the form of both the free metal and the aqueous complex is going to be higher, right? So again, you can affect solubility in such a case or in such cases, and I think we also discussed SORB ability. So in those cases where you are looking at adsorption or sorption, let's say, right, and you can, depending on the relative sorbability of your complex relative to or compared to just the metal, you can either decrease or increase the sorbability, right? Again, this is something that's a no-brainer, right? So we won't spend more time on that. And I believe we moved on to looking at developing some intuition based or intuition about the strength of the complexes. So in this case, obviously, right, and we talked about strength of the complexes. And so obviously multidentate will be stronger than the monodentate. Again, multi and monodentate, what are they about? So multi means you have a complex or a ligand with multiple binding sites, and monodentate is one with only one binding site, right? And thus obviously I guess the multidentate would in general be a multidentate complex would in general be stronger than a monodentate complex. And the second one, obviously stronger the greater the charge of both metal or ligand, let's say. So the greater the charge on your metal or ligand, the stronger in general the strength of the complex is. Again, that's a no-brainer again. And the third aspect is, I believe we talked about briefly about hydrated ion radius, right? And obviously, that's with respect to the concentration of the charge within a smaller radius, let's say, right? So the greater the hydrated ion radius, the greater the strength of the complex. Greater as in, obviously the concentration will be greater, concentration of charge when we have a smaller hydrated radius, right? As in within a smaller, what do we say, radius? I mean, this is a layman's description, I guess. Within a smaller hydrated radius, you have more concentrated charge, and thus you would have a greater strength of the complexes. And so we then talked about individual metal ligand interactions, right? As in, we classified metals as A metals or B metals, and then we listed the preference order of preference, right, with respect to the strength of complex for those these two kinds of metals, right? And one would form the ionic bonds, at least the A metals, I believe, right? Again, and then we started moving on to an example, and I believe the example we looked at was when we add aluminium to water, let's say, right, and the relevant complexes that need to be formed and such, or are formed, and how to go about understanding what are the concentrations of the relevant compounds at equilibrium, right? So in that context, we what did we do? We first listed the species, right? Al3 plus, H plus, OH minus, and the Al and different OH based complexes, right? Okay, keep in mind that in this particular example or scenario we looked at, we only had aluminum hydroxide complexes, right? So and then we chose the components. Components were, what is it now, H plus and Al3 plus, and then we wrote down the relevant formation equations, got down to the tableau, and then I believe we moved on to writing the total component balance equations, right? So total component balance equation, we got that from the tableau from the last class, right? So H total is equal to H plus minus OH minus, and so on with respect to the different species of aluminum hydroxide complexes. And Al total, again we have that here, Al3 plus plus AlOH2 plus, and the other aluminum hydroxide complexes, right? So again, obviously you can use, once you have H total and Al total, you can plug in the relevant values in VMinTech, and it will obviously give you the relevant concentrations of either the free metal, which is Al3 plus, or the relevant concentrations of the different aluminum hydroxide complexes, right? But obviously we need to also understand the fundamentals or the basics here, right? So let's just have a brief look about how to solve this by hand, right? So obviously here we have multiple unknowns here. Let's say how many unknowns here? 1, 2, 3, 4, 5, 6, and 7, I guess, right? Unless I missed out something else, but looks like we have 7 unknowns though. So how can I solve for them? Obviously, we need to look at the relevant equilibrium coefficient or equilibrium equations, I guess. And in this context, we talked about, or when we discussed the coefficients, equilibrium coefficients, we discussed that there are different nomenclatures out there, as in one for stepwise with the protonated or deprotonated, pardon me, and one for direct addition of your ligand, right? Again with respect to protonated and deprotonated, right? I think K and K star and beta star, right? So in general, as I believe we briefly mentioned or briefly discussed in the last lecture session, looking at beta star, let's say, which is the direct addition, I believe, right, of the protonated form of the ligand, would in general be easier for your calculations. So let's just try to write down some of the variables in terms of this particular beta star, and where would you have these particular relevant coefficients? Obviously in the relevant books, I guess. These are standard values more or less, right? Again, let's try to plug them in here. So let's say I'm trying to form various complexes here, right? So what would be the relevant direct step? Al3 plus H2O would be in equilibrium with Al, and let's say OH, and the charge would be 2 plus, and it would release 1 H plus, obviously. And I'm also having to form the other complexes, which I will list here, right? Al, OH, right? These are the 4, let's say, complexes that I am trying to form based on my direct and protonated ligand, right. Direct addition of the ligand in the form of the protonated ligand, right. And obviously we will then have beta 1 star, beta 2 star, beta 3 star, beta 4 star, right. Again, if you are not sure which complexes or how many complexes, let us say, a particular metal can form with a particular ligand, I would suggest, before you develop intuition, let us say, looking at the relevant tables, right, where you have the coefficients, and depending upon the number of coefficients listed, you can then estimate the number of and the kind of complexes that can be formed, right. So again, here obviously what else are we left with? So it's going to be Al3 plus 2H2O would be in equilibrium with AlOH2 plus and 2H plus, right. Again, this is direct addition, right. And obviously here it's a release of 3H plus. So it's going to be Al3 plus 4H2O, right, plus 4H plus. So obviously what is, let me just, so let's say if I'm looking at Al total, let's say, right, Al3 plus is what, let's say, I need to solve for initially, assuming that I know the Al total. So I need to express all these other 4 variables in terms of Al3 plus, right. So how do I do that, let's see. So I know that the beta 1 star, what is it going to be now? The concentration of AlOH2 plus into the concentration of H plus by the concentration of Al3 plus, meaning what is this now? So the AlOH 2 plus concentration can now be written as beta 1 star into the concentration of Al3 plus by H plus, right. So in the same manner, I can list the other, 3 complexes too, in the form of Al3 plus and the relevant coefficient, which is beta 2 star, beta 3 star and beta 4 star. Let us just list them out here so that we get some practice here, I guess. So Al, and the next one would be AlOH twice, right, and plus 1 charge. So that's going to be obviously going to be equal to beta 2 star into Al3 plus by H plus square, right. Again, that's from this particular equation. And what is beta? Again, a different type of equilibrium coefficient, right, a different form of expressing equilibrium coefficient based on the type of reaction. So it's going to be equal to the product of the activities of your products, right. So it's going to be AlOH twice plus charge to the coefficient, which is 1, into H plus to the power concentration of H plus to the power of 2 by Al3 plus. So that's why we end up with this particular equation here. And next up would be AlOH thrice 0 charge would be equal to beta 3 star into Al3 plus divided by H plus cube, right. And again similarly AlOH4 with 1 negative charge is going to be equal to beta 4 star into Al3 plus concentration by H plus concentration to the power of 4, right. So again here we can now express this particular equation in terms of just Al3 plus, right, by substituting the relevant equations here which we just developed, right. We can replace all these 4 variables here, this AlOH, all the concentrations of the complexes here in forms of Al3 plus, beta 1 star and H plus, right. So again similarly we can do so here, right, and then you will end up with 2 equations and 2 unknowns, right. So one would be H plus, one would be Al3 plus, and you have 2 equations and you can then solve for H plus and Al3 plus, and once you have that you can obviously calculate the species or concentration of the different species at equilibrium, right. So that's one way to go about that. So let's look at one other aspect here, let's see, and I believe we are going to look at recipe problems, right? And what's a recipe problem? As in, right, you know what it is that you are putting in initially, right? Have a solution, and I know what it is that I'm adding to the solution initially, and thus, or then I want to be able to estimate the concentration of the species at equilibrium, right? So let's see, let's look at the example that I'm going to have. Let's see, I believe again it's going to be based on Al3 plus complexes and H plus, right? But let me see what it is that we have. For example, we have 10 to the power of minus 3 molar, let's say AlCl3 plus 3 into 10 power minus 3 molar NaOH, right? So let's say here the example that I have here is we are adding 10 power minus 3 molar AlCl3 and 3 into 10 power minus 3 molar or 3 millimolar concentration of NaOH, right? So here again, based on some intuition or such, let's say, or some experience as you go by, you will see that Na plus and Cl minus, they are relatively non-reactive in solution, right? They are the respective salts. So we can neglect their or any further role in this particular scenario anyway. So based on that, let's see how to go about that. So what is H total going to be equal to now? What is the only source of H total here? Any H here? Not really. Any H here? Yes, in the form of OH, right? So it's going to be negative concentration of NaOH initially. So that's equal to minus 3 into 10 power minus 3 molar concentration, right? So with that, and the relevant equations similar to earlier, I guess. And what about Al total? Al total would be equal to what are the sources of Al total here? Anything in NaOH? No, right? Any Al in NaOH? Not really. Any in AlCl3? Yes. So it's 1 times AlCl3, right? And that's going to be equal to 10 power minus 3 molar, right? So based on the equations that we already had earlier, right? What can we express H total as? H total equal to, as we know, H plus minus OH minus, right? I mean, I'm just listing the equation, this equation, I guess, right? And we are assuming obviously that Na plus and Cl minus can be ignored now. I'm ignoring them, and which is not a bad assumption, at least when you're working it out by hand. And the equation I guess we have is Al OH plus 2, right, minus 2 times Al OH twice plus 1 charge minus 3 times Al OH thrice 0 charge minus 4 times Al OH 4 negative charge, right? And obviously what is H total here? H total equal to minus 3 into 10 power minus 3 molar, that's equal to H plus. And how can I express OH minus from our acid base chemistry background, right? What is it now? We know that H2O will dissociate and will be in equilibrium with H plus and OH minus. Kw will be the equilibrium coefficient for this particular dissociation, water dissociation, right? So we know that it's going to be equal to Kw by H plus, right? And how can I express these variables here now, right? And I can express them in terms of what it is we calculated out here, right? In terms of the various variables here, yes. And I'm going to plug that in here, minus beta 1 star into Al3 plus, right, concentration divided by H plus 2 times beta 2 star into Al3 plus by H plus square, right, by H plus square minus here, right, and minus 3 times beta 3 star Al3 plus by H plus cube minus 4 times beta 4 star Al3 plus by H plus to the power of 4, right. So here we have an equation with two unknowns, right. What are they? H plus and Al3 plus, right. So obviously we need another equation, and that equation is going to be from this particular equation, right, and let's just plug that into. So we now have Al total, and what is Al total in our case now? Al total in our case was 10 power minus 3 millimolar, or 10 power minus 3 molar, pardon me, right. That's equal to Al3 plus, right, and what else, plus beta 1 star into Al3 plus by H plus beta 2 star into Al3 plus by H plus square plus beta 3 star Al3 plus by H plus cube plus beta 4 star into Al3 plus by H plus to the power of 4. So again we now have a second equation with two unknowns. Again they are Al3 plus and H plus, and here we had another equation with H plus and Al3 plus. So two unknowns and two equations. So now you can end up solving for your particular solution, I guess, right. So by using the relevant coefficients, in which in this case for beta star, and knowing the initial concentrations which we had in the form of AlCl3 and NaOH, we can now solve for the solution, and once we get H plus and Al3 plus, from them we can calculate the concentrations of the different complexes again, right. So that's something that we can be done with. So let's say we can move on to the next example that I have here. So let's say I have an example related to fluoride complexes. So instead of just aluminum hydroxide or an aluminum hydroxide based complexes, we are now going to have fluoride complexes, I guess. So let's see how the situation is going to differ now. Aluminum, right. So obviously here we need to first identify again the species, and then move on to the components, write the formation equations, the tableau, and then the total component balance equations. From that you can then express the different variables in terms of the, let's say, simple variables that you are looking at, which would in this case be H plus, Al3 plus and F minus. So we will just look at that very briefly here. So what are the species going to be? So obviously you are always going to have H plus and OH minus, and then the metal, right. And what else? Let's say you will obviously have F minus, fluoride, and then we are going to have the aluminum hydroxide complexes, which we discussed earlier, right. Al, and we know that I guess we have 4 of them, right. And then moving on to the complexes of fluoride, I guess aluminum fluoride, AlF2 plus, AlF2 plus, and AlF3 not, and AlF4 negative, right. And with this, am I done, or are we done? So here I guess one aspect that we need to look at is we have listed all the complexes, right, with aluminum and hydroxide and aluminum and fluoride, right. But keep in mind that the acid base reactions, the aqueous complex, redox or precipitation and dissolution, they do not occur independently, right. Once you have equilibrium, let's say, you will have all the other reactions happening or going through simultaneously. So obviously in this case we do not have any redox reactions, and we are not considering precipitation at this stage, but we do know that acid base reactions are going to occur, right. So here let's say you can, depending on the pH, also have the conjugate acid for F minus, let's say, and that's going to be HF, right. So that's something we need to keep in mind now. So they are not just F minus, depending on the pKa value, right, of HF dissociating into H plus and F minus, right. You will also have the relevant conjugate acid and base, right. So that's something that we need to look into as we keep progressing through the course. Let's say you need to understand that all the relevant reactions are going to occur simultaneously. So depending on the situation, which is the case here, you will also need to look at the relevant acid-base reactions too. So let's just have the formation reactions. Before that, obviously we need to write the components, right? And the components are going to be H plus, Al3 plus, and F minus, right? And with just these three components, we can form all the other species, yes. So now let's say I'm going to have the formation equations. So once you have the relevant background, you can do away with this formation equations, but for now we are going to list them here. So H plus, so first I'm going to list all my species here, let's say. So H plus, how can I form my species from the components, right? Al3 plus, F minus, and for the sake of time, let's say I'm going to neglect the aluminum hydroxide complexes because we already discussed them in detail in the last class, and obviously you need to list them too, but I'm going to not list them here. I'm only going to list the aluminum and fluoride complexes here, right? And AlF3 0 charge, and AlF4 negative charge, and HF. And now let's see how I can form my species from my components. So on the left hand side, I'm going to have my components. H plus, 1 H plus would lead to 1 H plus, and H2O minus H plus will lead to OH minus. Al3 plus would lead to Al3 plus, F minus will lead to F minus. So now here I am going to come up with a relevant aspect here, right? So how do I go about it? Again, as we mentioned, we need to look at hopefully expressing beta star, right? So it's going to be Al3 plus, right, plus what is it now here? F minus, that's it here, I guess, right? That's going to be equal to AlF2 plus, and the other one would be Al3 plus plus 2F minus, right? And that's going to be equal to AlF2 plus 2H plus, is it? Not really. So Al3 plus 3F minus is equal to AlF3 naught and Al3 plus, right? And plus 4F minus is equal to AlF4 minus, and HF is HF plus F minus, right? So I'm neglecting again these three species, not neglecting, I haven't listed these 4 aluminum hydroxide species because we already looked at that earlier. Now I'm going to move on to writing my tableau. So in the tableau, I need to first come up with my components here in the columns, right, and F minus, and here I'm going to list all the relevant species here. So H plus, OH minus, Al3 plus, F minus, and assume that we are already writing down these 4 species here, these 4 as in aluminum hydroxide species, right? Or let me list them for sake of understanding, I guess, right? And so on, I guess, right? So again, from these particular equations here, we can, from the formation equations, we can fill out the tableau. So that's going to be H plus minus 1, 0 here, 0 here, and we know it's going to be minus 1 here, minus 2, minus 3, and minus 4 here, right? With the Al3 plus, it's going to be 0, 0, 1, 0, 1, 1, 1, 1, and 4 species of the aluminum fluoride complexes, right? AlF3 naught and AlF4 negative and HF. So it's going to be equal to again 1, 2, 1, 1, right? And 0 here, and 0, 0, 0, 0, 1 and F minus, right, and obviously 0 here, OH minus 0, Al3 plus 0, 1 here and 0, 0, 0, 0 here. But from here we need to look at these particular equations here. So it is 1F minus for AlF2 plus and 2 here, right, and 3 for AlF3, 4 for AlF4 and 1 for HF, right. And again, so we just looked at a particular a relevant example where we have not just aluminum hydroxide complexes but aluminum and fluoride complexes. So just to be able to understand what goes on, right, I listed the relevant formation equations and then the tableau in great detail. So from here obviously what can we do? We can apply the H total and then again Al3 plus total, right, and F total, right. So from here we can just get that done relatively easily, which I am not going to go through again in detail, right, F total. But obviously you need to be able to come up with the relevant coefficients. So the way we wrote down the formation equations, you might need to change them slightly if required, because I guess we had the protonated form addition here, right, in this case of what is it now, or deprotonated form addition, but beta 1 star would require the addition of the protonated form of the ligand, which is HF. So then you would have minus H plus here. So that's something you need to take into account, right. Again, so with that we will end today's session, and in the next session we will look at a few examples where we will look at Vimintek and also application of this particular aqueous complexes, I guess, right. So with that I will be done for today, and thank you.